My name is Andy Robbins. This is Will Schrader. We're going to introduce ourselves a little more in depth. The title of our talk is An Ace Up the Sleeve, Designing Active Directory DACL Backdoors. We're super excited about the talk. We hope that you enjoy the content.
This is our first time at Black Hat. Our first time speaking at Black Hat. Happy to be here.
Super excited. This is me, Andy Robbins, also known as Waldo. I work at SpecterOps as the Adversary Resilience Lead. I'm a co-founder and developer of the Bloodhound project. I've done training, I've done presentations, and if you're a financial geek, I would love to talk to you about ACH and how awful that whole platform is.
So my name is Will Schrader. My handle is Harmjoy. I'm an offensive engineer with Andy at SpecterOps. I've written a lot of code. I'm the co-founder or developer on Veil Framework, Empire, PowerView, PowerUp, Bloodhound, Key Thief, a whole bunch of stuff. I've presented a few places, been a trainer, and I'm an active PowerSploit developer, and I'm a Microsoft PowerShell MVP. So somehow Microsoft doesn't hate me enough that they decided to at least make me an MVP.
Okay, so let's give you an idea of where we're going to go. So we're going to start off by talking about DACLs and ACEs, what these are, how they work, why they matter. We're going to talk about common misconfigurations and how those misconfigurations can be abused for PrivEsk and for backdoors. We're going to do a demonstration of how to analyze these more easily using the Bloodhound interface. Then we'll go through our case studies of designing the ACL-based backdoors. We'll show some examples of some of the things that we've thought of and some of the things that other people may have thought of already. And then at the end, we'll talk about defenses that you may be able to implement to find some of this stuff. So, important disclaimer, we're not dropping ODE, we're not talking about anything worthy of a CVE. This is a way to abuse the Windows security model in a way that we think is pretty interesting. Secondly, and maybe more importantly, is while ACEs and ACLs can be used for elevating rights, what we're talking about is post-escalation and burrowing yourself into an Active Directory domain once you have become domain admin, and how you can implement malicious ACEs to have long-term code execution lists persistence in an environment.
Cool. So why should you care about this? So there's a few really cool things that go along with this type of persistence methodology and this type of approach. So one, it's often very difficult to determine that if you find an ACE that can provide elevated access or additional access into the future, if you find these malicious ACEs, it can be difficult to actually tell, are they actually malicious or were they implemented by accident, either through some third-party installation or who knows. Also, these types of backdoors have a minimal forensic footprint. It's difficult to even find them, and we're going to make it even harder to actually find them later in the deck. They often survive operating system and domain functional level upgrades. And they're very subtle, so this gives you an excellent chance for long-term, multi-year subtle domain persistence. And a big point here is these may have been in your environment for years, which kind of terrifies me once we started thinking about it. Because, and I love this quote, Mac Graber, he used to be my boss about a year or so ago, and he spoke 2 years ago at Black Hat on WMI, and he had this great quote saying, as an offensive researcher, if you can dream it, someone has likely already done it. And that someone isn't the kind of person that comes and speaks at security conferences. So please keep this in mind once we actually get to the case studies. We're going to go through this background and everything so you have the understanding. And then hopefully we'll bring it all together and show you the really, really cool things you can do creatively with this type of stuff.
Okay, so let's do some background information. And first of all, we need to acknowledge some previous work that came before us. Most importantly is this project from ANSI, which is the French equivalent of the NSA. They had this project called Active Directory Control Paths. They did the white paper regarding how ACEs can be abused, and they also used graph theory to map out the connections that can go from any arbitrary place in the domain to another. So they also served as initial inspiration for us when we were developing Bloodhound about a year and a half ago. Luca Boyot and Emmanuel Gras, we want to make sure that we mention their names. They're the ones who developed the Active Directory Control Paths project. Secondly, the DACL scanner, we should acknowledge this work as well. This is a GUI interface based on PowerShell scripts that you can use for scanning ACLs in Active Directory. It does things like CSV export, CSV diffing, some cool things like that.
They also have a really great blog post there, and again, these slides will be public, but they go into some details of a lot of the control relationships that we cover as well.
That's a project that's developed by Robin Gramberg at Microsoft. Next, when we started doing the initial research for, like, can we find an example where somebody has used ACLs for putting a backdoor into Active Directory already, we came up pretty empty-handed. We couldn't find a whole lot of examples. This was the closest thing that we could find. It's a Russian blog post from 2010 about how to use ACEs to obscure the existence of objects. So it served as an inspiration for our talk, but we think we've built on what this blog post went into pretty well. And when you're looking at different ways to attack an environment, if the only existing writing that you can find is in Russian, you're probably on the right track.
Yeah. So, a little bit of this background, what we mean by securable objects and DACLs and all that. So, securable objects in a Windows environment and Active Directory or on the host are defined by objects that have a security descriptor. This is a binary structure that's stored. It has several different pieces. So it has the primary group, the owner, SACLs, and DACLs. And we'll go over all the terms here in a second. This can also be described as a security descriptor definition language string, so an SDDL string, but we're not really going to cover that. So the thing we care about here mostly is the DACL, what we'll be covering. So a lot of people use these terms interchangeably. We use kind of ACL and DACL interchangeably, but the access control list is actually the superset of the SACL and the DACL. So DACL being the discretionary access control list, and the SACL being the system access control list. It's a pointer to an ordered collection of access control entries, or ACEs, that are stored for the object. So the DACL is what actually defines who has what rights, what principals, who has what rights over a particular object. So it's just the access control model. The SACL allows for auditing of success and failure auditing on accesses to different components of the object, but we're not really going to cover that in this presentation. So ACEs include a series of flags that control auditing, a little bit of inheritance, and they have the principal, so the SID of the user that has the right. We care about that very much, and we'll get into it why. And it also has a 32-bit access mask. And we're not going to go and dive super deep in the access mask. We actually have a 64-page white paper that'll be published by Black Hat that goes into all this stuff in way, way more depth than we have time for. But the access mask actually controls, who has what are the rights that this person has? They can be very, very granular, and we'll get into extended stuff here in a second. But in ADUC, Active Directory using computers, is what it looks like. So the harmjoy user, the principal, that'd be stored in the SID. The object itself is victim. And the rights here is they have modify permissions and modify owner. There's one bit in the access mask we definitely care about. It's a DS control access. It is a bit that grants privileges in the access mask, or it's a bit in the access mask that is used to demonstrate privileges that aren't easily expressed already in the access mask. So it's a way to extend how you can actually define this stuff. So this bit is interpreted two different ways. If the object ACE type, which is a GUID, if the target of the ACE is a confidential property name, so if it's mapped back to a property that's marked as confidential, for example, laps, then flipping the DS control access bit will grant read access to this sensitive property. All right, so hopefully it makes sense, right? It's not too crazy. The second way is if the object ACE type is a GUID that's mapped to an existing extended right in the forest schema, then a specific granular right in Active Directory, and this is specific just to Active Directory, then a specific extended right is granted. For example, I don't want complete control of the object, but I want the ability for help desk to force reset the password, but I don't want to give them any other rights, right? So that's not easily expressed in the existing access mask structure. So they flip the control access bit. That target GUID is going to map in the Active Directory schema to user force change password. Also, say DC sync rights, like replication rights, which we'll get into in some of the demonstrations.
OK, so we have the DACL, we have the ACEs. The DACL is a collection of ACEs that are listed in what is called canonical order. So if you've ever looked at like a firewall ACL, you know that the firewall reads the ACL from the top down. And from the top down, whatever rule is relevant to the access that is being requested is the rule that hits. In Active Directory, it's very similar. However, there is also inheritance and overriding permissions that we have to consider. So in the Windows security model, the kernel mode security reference monitor is the part of the operating system that actually evaluates the DACL in canonical order, and it makes the access decision of whether access will be granted or denied. This becomes important when we're talking about adding our own malicious ACEs, because we can take advantage of the order of inheritance and the order of evaluation that the SRM uses, and we can abuse that in a way that lets us do very, very sneaky things that we'll talk about in a second. So let's take a look at this example. We have this OU here called IT. Under there is an OU called help desk, and under there is a user called Robbie Winchester. I'm going to put an explicit deny on this IT OU, and explicit deny for full control, let's say, for example. That's going to inherit down to the OU under there, and on the OU there, it's going to be reflected as a inherited deny. It's also going to inherit down to the user, and it's also going to show up there as an inherited deny. What if in the intermediary OU on help desk, if I said, well, wait a minute, I want to have an explicit allow. That explicit allow is going to override the inherited deny, because explicitly defined ACEs override inherited ACEs. There's one final complication with this. So that explicit allow is also going to be inherited down to the Robbie Winchester user. Now, because the OU called help desk is generationally closer to the Robbie user than the OU called IT, the ACE that it inherits from its closer OU parent is the one that is canonically higher in the DACL. Finally, if we define explicit ACEs, those also override inherited ACEs. So what you wind up with is on the Robbie Winchester user, at the very top, we have explicit deny. That will override anything else, with the exception of the object owner, which maintains full control. Then the explicit allow, then the inherited allow, and then finally the inherited deny. We're going to abuse this further in the talk. I'm going to show you how to do that. So let's take a look at some basic misconfigurations and how we abuse these. Before we take a in-depth look at that, one thing to repeat is that we are focusing this talk on persistence, not escalation. So everything that we're talking about requires some kind of privilege to implement these malicious ACEs. Domain admin is the easiest one because domain admins control everything, or you need to have control over the object that you're backdooring.
And in general, we want to chain ACEs or build these in that you can go from lower, less privileged objects or principals to higher privileged ones. So we're going to go from a domain authenticated user up to domain admins, or a specific user that's not in any privileged groups, allowing them elevated access to take back over.
So in Active Directory, obviously, we have different kinds of object classes. One of those are users. So if we have an ACE against a user that allows us to take over that user, there are basically two options that we know of right now. One, the most obvious, is the ability to change that user's password without knowing its current value. This is what you give help desk people so that they can reset someone's password after they lock their account out. The second one is targeted Kerberoasting. So if we can write a value to the SPM property on the user object, we can Kerberoast that user from any domain user in the environment. We can get a Kerberos ticket back from the domain controller for that user, which is encrypted using the NTLM hash of that user's password. Then we're just cracking NTLM. If we can do that, we can recover the current clear text value of that user's password.
Then we can reset it, and the user is none the wiser. So it's not destructive in that there's an indication that a property changed, but the end user doesn't actually notice anything different.
Secondly, we have group objects, obviously. So the primitive that we're looking at here is the ability to add an arbitrary object to the members list of a group. Then we write the existing privilege that that group has, either by security group delegation or by that group being, for example, a local admin on a computer. We can either have the ability to write to the members property, or we can have the generic write privilege, and that allows us to do this.
And again, all throughout this, we actually have weaponization functions through PowerView to actually abuse all these takeover primitives.
Yep. In this instance, it's add hyphen domain group member. Computer objects are unfortunately a little less sexy.
Yep.
So computer objects, we do know how to take over these if Laps is installed in the environment. Laps is the local admin password solution from Microsoft, which you absolutely should have deployed. Laps changes the local admin password for the computer and then puts the clear text value of that password as a protected attribute on the computer object. If we can read that attribute, we have the local admin password. Make sense? That's about it as far as we know of how to take over computer objects. We are very interested in what others may have as far as ideas for how to do that.
Definitely.
It's an area for future research. Next, every Active Directory domain has a domain object that represents the domain as a whole. So the domain object itself, if you have full control or if you have DS replication get changes and DS replication get changes all, then without any other kind of privilege, you can DC sync. So let me say that one more time. Without having a local admin on a DC, without being a domain admin, if I have certain privileges on the domain object, I can DC sync, get NT hashes for any user in the environment that I want, including krbtgt, anything.
So again, we care about write DACL, which would allow us to modify the security information to then grant ourselves those rights.
Exactly.
So GPOs, group policy objects. The main takeover primitive for GPOs involves the right to edit the GPO itself. So these group policy objects are collections of settings that are applied to OU sites and domains. Those are then filtered down through the inheritance that Andy talked about, kind of like ACEs. And these settings are applied to user and computer objects all the way kind of down the chain. So if you have the ability to edit a GPO, there's 1,000,001 ways to turn that into code execution on a computer it's applied to, or to modify something about the user. You can change reg entries, schedule tasks. There's 1,000,001 things. So for this, what we care about is writing to all the properties, or writing to GPC file syspath, which is this write. If you have the ability to modify GPC file syspath, those permissions are actually cloned down, from what we can tell, onto the file system in sysvol where the GPO actually resides. So modify it, clone down, and now I have the ability to actually edit the GPO files that are actually on sysvol. Then there's a few generic rights that are applied to pretty much all the objects we talked about. So those are kind of the object-specific takeover rights. These are the generic ones. So generic all grants us all rights. Pretty simple. It also grants control rights, which we're going to talk about on the next slide. Generic write will allow us to modify almost all properties, everything but confidential properties on the object. Everything except things that are protected by that DS control access bit, that type of thing. These are both abusable with set domain object, and these two rights, again, apply to pretty much almost anything we talked about for takeover. And again, the paper has more specific details. So what do we mean by control rights? There are a couple of rights that will allow a trustee or principal to take control of the object in a specific way instead of modifying the actual object itself. So write DACL will grant us the ability to modify the DACL, right? It is abusable with power view with add domain object ACL. And write owner grants us the ability to take ownership of the object in Active Directory. And the reason we care about this is that owners have implicitly complete rights on the object, even if there's an explicit deny. So even if Will has complete deny on Andy, if I'm the owner, then I have complete full access. And this is abusable with power view with set domain object owner.
OK, so let's take a look at how we can analyze this stuff with Bloodhound. Unfortunately, if you try to audit ACEs in Active Directory, you go down the path of a very frustrating experience currently. We think that we've done a pretty good job with implementing these ACE edges into Bloodhound. One thing to note is we're only implementing the abusable ACEs. We're not pulling in every single ACE on every single object.
It's also not 100% complete. There's a few additional control relationships, specifically GPOs, that we're in the process of implementing.
So as for defenders, we hope that this is useful for finding malicious backdoors, for enforcing least privilege, and for hopefully detecting some of the non-stealthy DACL-based backdoors. As attackers, we can use this for finding opportunities where if we have a user that is multiple degrees of separation away from the object that we're actually interested in taking over, we can backdoor this user, which may not be as interesting to the defenders, and we have access to this other object, which is. We can also have an understanding of what the current privilege maturity level is in the environment so that we know just how well we can sneak in and blend in with the noise. So we have a video that we're going to show you. This is the Bloodhound interface that we're going to look at. When you pull up the Bloodhound interface, you see the members of the domain admins groups, which we unroll out for you. So if I click on the domain admins, I'm interested in seeing inbound object control. So
this was released with the 1.3 update.
The explicit object controllers, we can see that there are 6 groups that have some kind of control over the domain admins group. 4 of them are a generic all edge, which is full control. And 1 of them is a write DACL edge, meaning that I can take control of the domain admins group. So we have the exchange groups, and then we have this administrators group and a backup too. There are users that belong to these groups. If we unroll that out, we can see this is what the picture actually looks like. And so all of these principals here actually have control over the domain admins group via security group delegation. The exchange trusted subsystem is one of particular interest to us. This user here is a member of that group, which 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 has the right DACL privilege to the domain admins group. What we can also do is look at inbound transitive object control. So by only manipulating these ACEs, or by executing an ACL-only attack path, who else in the domain can take over the domain admins group, or any other group, or any other principal that we track? In this instance, we have a group that belongs to a group that has force change password ability to this user called B. Schaffner, and that user is a part of the domain admins group. Slightly more interesting attack path. Starting at this user, we use its group delegation from this group to the following group. That gives us the ability to change the user password for this user here. That user can then in turn change that user's password, who belongs to this group to the right, and that group has full control of the domain admins group.
Is that it?
There's one more little thing. So what we're also interested in is outbound control. So obviously domain admins is going to have control of everything, or at least they should. We can also look at a supposedly low privilege user and find what its privileges are. So our tailor will look at the outbound object control section. First degree object control is 0, so the user itself is not defined as a control principal on any other objects. By security group delegation, it actually has the ability to change 4 different users' passwords. So because he's a member of this group and then a member of the following group, he can change these 4 user passwords. Now, outbound transitive object control. What principles can this user take over by executing an ACL-only attack path? And we follow that tree out as far as we can go. And we're basically looking at every edge in the Bloodhound database except for admin rights to a computer or a user having a session on a system.
So again, don't need code execution on any additional system to run these types of attacks.
Yeah, all of this is just communicating with the domain controller, and that's it. That's it for the video.
Right.
All right, so that brings us to section 4, designing these Active Directory DACL-based doors. So what our objective is here, we want to implement a ACL-based backdoor in Active Directory that allows us to get access into the network at any time later in any user context and very, very quickly upgrade our rights to whatever privilege we want, domain admin, for example. We want to either blend in with existing ACLs so that it's very hard to tell the difference between our malicious ones and quote unquote good ones. And we also have other primitives for making that very, very hard for an auditor to actually find. The first of which is the ability to hide the DACL from enumeration by an auditor. So this requires 2 steps. Will has made the point already that if I am the owner of an object, I retain all privileges regardless of what other ACEs exist on that user's DACL. So I need to change the object owner away from domain admins to some other principal. And then I need to add a new explicit deny ACE, which is going to override everything else.
Remember that SRM inheritance?
Yep. And what I'm going to do is the everyone principal, I'm going to say they are denied read permissions. So now if you do like AD ACL scanner, or if you look in ADUC, you're not going to be able to even read the DACL on the affected object. This is what that looks like in the ADUC GUI. So what I'm saying is that everyone is denied read permissions against this user called Jeff Dimmick. Make sense? What I can also do is I can hide the existence of a principal. This can be any principal. This can be any object in Active Directory. I can hide the fact that it actually exists. This is a little more complicated, but it's basically 3 steps. The first of which is change the object owner to some other principal, either itself or a principal that we have control of or that we can gain control of. Then grant explicit control of the principal to itself or some other control principal. Then on the OU that contains this principal, we're going to deny everyone the list contents privilege. So in ADUC, via LDAP, with the net executable, you're not going to be able to see that this user even exists. I assure you that a user exists in this OU. However, running as a domain admin and looking in ADUC, we can't see it.
And whether it's LDAP, PowerView, ADUC, DS query, it doesn't really matter.
Right. So to sum that up, we know how we can take over other objects in Active Directory by abusing ACEs. We know that we can control who can enumerate the DACL to find these backdoors that we're putting in. And we know that we can hide the principals that we're backdooring or otherwise from easy identification from defenders.
Okay, that's all the background, all the pieces, all the Lego pieces we're going to put together. So remember, if you can dream it, these are the 5. We're going to go over 5 case studies that we came up with. We already have more ideas after you put the deck together. There's infinite possibilities on how you could design these chains of malicious ACEs. So the very first one, pretty easy. I talked about those DC sync privileges. So what the attacker does to implement the backdoor is they add DS replication get changes and DS replication get changes all to the domain object itself, where they are the principal, or a user they control is the principal. Then that user or computer, doesn't matter what it is, does not have to be in any groups at all. It doesn't have to be in any privileged groups. It doesn't have to be domain admins. It doesn't have to be anything. You just leave it there. Then the attacker in the future, it could be 5 years in the future, 10 years in the future, regains access to that account and then can use DC sync, again, written by Benjamin Delpy and Vincent Latude. Thank you very much for DC sync. They can synchronize the NTLM or AES or whatever credential material from the domain controller. So we'll show you a demo. And again, with all these case studies, we're going to start off simple and we're going to get pretty crazy by the end. OK, so walking through this. All executed ACL based from one pivot point. We're going to import PowerView, and we're going to use this bad guy user as our principal. He's our attacker. So first, we're going to show that we guarantee this bad guy user is in no privileged groups. He's just in the domain user's default group. We're going to save off the SID of this bad guy. And then we're going to enumerate the current ACLs of the domain object, filtering for that SID, just to show you there are no explicit ACEs on the domain for that user. Now, using PowerView, add domain object ACL, we are going to grant bad guy the rights to DC sync on the domain object. And again, you need domain admin rights to implement this backdoor. We're going to ensure the rights are set. And now we're going to, oh, yep, you see DS replication get changes all. That SID matches. So our attacker now has the rights to DC sync any account in the entire domain. I'm going to switch over, and you see up here, I have an execution running in the context of bad guy. I tried to DC sync previously. I got nothing. But now after I implement the backdoor, I have the ability to get this sensitive key material. So kind of cool. Nothing too crazy yet. All right. So the next one. We won't go into all the detail for admin SD holder, but a quick summary is it essentially functions as a permission template for sensitive accounts. So the backdoor is an attacker grants either force change password or generic all on the admin SD holder object, this very special object in Active Directory. Then every 60 minutes, a special process called the Security Descriptor Propagator Process, or SDProp, will run, and it'll take the permissions that are on admin SD holder, and it'll take those and clone them to every single protected user and group in Active Directory. Enterprise admins, account operators, domain admins, things that are usually identified by admin count equals 1. Then the attacker hides their account, their principal, their own account using the methods described. So to execute, the attacker just whenever they want, 5 years from now, force resets the password for any domain administrator in the entire domain. And the cool thing with admin SD holder is if defenders find the that backdoor on one domain admin, if they don't fix it on an admin SD holder and they aren't aware of it, then SDProp will just go put the backdoor back in for you. So again, we're starting from a different user this time, bad guy 2, load up PowerView, do the same steps. And we're going to show the OU location for the bad guy user. It's totes not evil. So this is so we can hide it later on from enumeration. Now we're going to grant the bad guy to all rights, generic all rights, onto the admin SD holder object, using, again, PowerView for add domain object ACL. Then we're going to change the owner of bad guy 2 to himself. So the first part was the backdoor, and now we're going to hide the principal. So change the owner. We're going to get some pointer, basically some references to the raw objects of the user in the OU. Then we're going to add a custom ACE that denies the everyone SID S110 the right to enumerate the object itself directly. So if we do this and leave it now, domain admins could still see the existence of the object in ADUC, but they couldn't interact with it. Now we're going to deny everyone the right to list the children of the OU that the user is a part of. So deny, list children, that same S110. We're going to commit those changes. We're going to wait 60 minutes for SD-prop to run. We're back. We're going to check if those rights propagated to a domain admin named DA. We see OK. We see the SID 1173. Now, domain admins could still enumerate the DACL on this. But the domain admin cannot find bad guy 2 through LDAP searching. It's not there. Now, I'm going to refresh an ADUC, and that guy disappeared. Even though he's still there, I can still log in as him. And I still have the ability now to use bad guy 2 to force reset the domain admin password using PowerView again. And now I can do a run as for the DA and log back in. And I can do this for any protected user in the entire domain. And then if you even try to resolve the SID, domain admins can't even resolve the SID for this in the principle. So kind of cool. Little cooler, right? Using some of those stealth primitives. All right. That was exploitation. All right. So LAPS. We don't have a video for this one, but LAPS is Microsoft's local administrator password solution, like Andy mentioned. It's basically a set of client-side extensions and schema extensions that allow the computer to change its password to a local admin password to a random value every 30 days, and then it stores that in that MCS admin password attribute that's protected by DS control access. It's administered by these admin pwd ps commandlets. There's a specific function that they provide called find admin pwd extended rights, which you can audit who actually has these MCS. So the problem is this commandlet was built to enumerate the typical ways these rights are delegated through normal processes in Active Directory, which makes sense. It was not meant as a security audit type protection. It was meant as, oh, you ran through normal delegation for LAPS and you found, OK, here's who you actually delegated to. So here is actually the not comprehensive list, because we found some a little bit more after we submitted the slides, and the white paper actually is updated for it. But these are most of the cases where someone has the ability to read the admin password. You have the DS control access, and there's several inheritance cases, generic all, because that's going to imply all these extended rights, and then object control. Are you the owner? Can you modify the DACL, and can you modify the owner? Unfortunately, the official commandlet misses a couple of things. There's a couple of logic flaws. So DS control access, if it's there on the OU and is inherited, if it's inherited to all descendant objects instead of just computers, that is not checked for. The owner isn't checked for. The write DACL and write owner isn't checked for. And also, it only analyzes OUs and optionally computer objects in those OUs. It does not analyze the default container for users and computers. So those can still have LAPS installed. So example. A normal user can't read the MCS admin password. This is what we want. This is normal. So we have John Smith. He can't, at the bottom there, get domain computer for exchange. He can't actually read the password. And you see, running that LAPS commandlet to find admin password rights for servers, you see under extended rights holders, we have system, domain admins, and server admins. So that shows that John is not part of server admins because he doesn't have that group delegated right. Now we add a malicious ACE entry. And again, it's a lot of text. We explain it step by step in the white paper. We're going to add a specifically crafted ACE that exploits the inheritance flaw. We're going to add this to the OU. So this is going to propagate down. And now a domain user at the bottom there, that same guy, John Smith, can read the local LAPS password for any computer in that OU. But the official commandlets don't actually show John Smith is actually showing up as a delegated access holder. So you could set this right to these computers that have LAPS installed, and everyone thinks it's protected, and your administrator or your attacker account has the ability to read the local admin password and recompromise any of those machines at will.
OK, so I'm a little bit biased, but this is my favorite one. Mine's
the last one.
This has to do with the Exchange server installation process, which if you've ever done that, you know how challenging that can potentially be, especially the upgrade process. So when you install Exchange Server, multiple things happen. Exchange adds many security groups to the domain. It extends the Active Directory schema. It adds properties to several different object classes in Active Directory. and it gives itself full control over several objects in Active Directory. Used to be including the admin SE holder, the domain object, domain admins group, etc. Now, with Exchange 2016, with Exchange 2013, and with Exchange 2007 SP1 and forward, it's every object in the domain has full control over, with the exception of anything that has that admin count equals 1.
So anything protected by admin SD holder.
Right, exactly, yep. Before 2007 SP1, Exchange gave itself write DACL to the domain object, and we have seen in multiple real environments where these groups have full control of everything, including the domain object, including the domain admins group. So here's how this backdoor works. What we're going to do, we're going to ride the existing privilege that Exchange has, and we're going to backdoor an object that has the same privilege by security group delegation. So this is going to be extremely hard to find. First of all, we're going to find one of these non-protected security groups that has local admin rights onto an Exchange server. The Exchange servers, when you install Exchange Server in Active Directory, they're added to a group called the Exchange Trusted Subsystem. Yeah, it's a mouthful. That group then will have all of that control in Active Directory that I was enumerating before. We're going to grant authenticated users full control over that security group that has admin rights to the Exchange server. We're going to change the owner of the group to the Exchange server. And then we're going to deny read permissions on that group to the everyone principal. So nobody's going to be able to see what the DACL is on this group that we just backdoored. So how do we execute this? First of all, we're going to regain access to Active Directory. We're going to, and we can do this as any user. We're going to add ourselves to that backdoored security group. Then we're going to use our newfound local admin rights on that Exchange server to execute commands as the system user on that computer, which when you do that, you have the same privileges that the computer object in Active Directory has.
So yeah, so for any network traffic, when you're running a system, it's going to use the computer account for the actual LDAP traffic in Active Directory.
And so, like I said, because many times the Exchange Trusted Subsystem has full control of everything, that means that the Exchange server itself can DC sync. So we have a video of this.
This one is pretty cool. And there's our last video. Let's see. All right.
So again, here's the Bloodhound interface. And what we're going to do is we're going to find the security group that we want to backdoor. So the domain admins group, we're going to look at transitive object controllers. And here we have the Exchange Trusted Subsystem, which is populated with the Exchange servers. Then we will select one of those Exchange servers, and we're going to see who it is that has effective local admin rights against that box. So we're going to do Exchange 001.
And again, this is how Bloodhound can be used to plan these types of backdoors.
We're going to look at who the unrolled admins are against this box, which there are 7 users that have local admin rights. Going from right to left, that's the computer. Then there's a group that has admin rights. Then you can see a group is belonging to that group. And then again, there's a third group that belongs in this nested group structure. This group here, server backup tier 2, this is the group that we're going to backdoor that's going to give us access to everything. Again, we're going to import Power Review. And we're doing this as a domain admin. We're installing the backdoor. We're going to get the raw directory entry for the object, for the group. We're going to grant authenticated users full control of the security group. Then we're going to change the owner of the object to an Exchange server, just the same Exchange server that we're going to be targeting for our backdoor. Done. And then finally, we're going to deny read permissions on this group to the everyone principals. So this is an anti-audit measure that will make it difficult to find this backdoor. And that's it.
Come back a year later?
Yeah, we come back a year later. We're on this computer called Windows 8001 as some user called Robbie Winchester. Because we have full control of the server backup tier group, we're going to add ourselves to that group. Done. Now we're going to use psexec, and we're going to run mimikatz on the remote system in the system user context. There are obviously better OPSEC ways to do this. Now we are running as a system user on that Exchange system, and we're going to use that privilege to DC sync the curb TGT account, and we're done. Now we have the NT hash of the curb TGT. We can create a golden ticket. We own the entire domain.
Yep. thanks again to Vincent and Benjamin.
Yes, thank you, Vincent Litsu and Benjamin Delpy.
All right, so there's one last scenario that we don't have a video for because it's so kind of complex, but I'll try to talk through it. So again, you can do chains of this stuff. You can let your imagination go wild. So the backdoor for this is the attacker grants them his or herself generic all to any user in the domain. That user doesn't have to be privileged. It can be anybody. And then you grant that kind of patsy or proxy user write DACL on the default domain controller's GPO. That's the entire backdoor. So what I like about this approach of using kind of a proxy or a patsy user is that even if incident responders or domain admins find the backdoor for the write DACL on domain controller's GPO, they would then have to walk back as saying, oh, is there actually a chained backdoor to this user, which is what we have with generic all. And you think about it, you could go back 7 levels, right? You could have force reset passwords and generic all the way down the line. So you have to model the entire system in order to find these types of things, because we're basically building attack chains out, and it's going to get harder and harder and harder because every time it's going to branch out with possibilities, and they would have to investigate every single option. So for execution, the attacker grants this proxy user, or they force reset their password. Then they use that access to add a new DACL to the GPO because they had that write DACL permission. So they add a new DACL that grants the patsy user that GPC file syspath modification. So we have the ability to modify the access control information, and we're using that to grant ourselves the right to actually modify the GPO itself. Then the attacker uses that account to grant SC-enabled delegation privilege to the attacker. And I wrote some stuff about this, and there's some other information about this for constrained delegation type attacks. Don't have time to go into it, but it's super, super cool. But end result is, with that GPO is pushed down. The attacker user now has SE delegation privilege on the domain controller, and it can modify the MS allowed to delegate to parameter, and then they can use Mimikatz and Kikyo to actually execute a constrained delegation attack and then DC sync or gain complete access or to the entire domain and recompromise the domain controller. But again, that's really subtle, right? It's just generic all. You just need rights to one user, and then you chain this stuff back, and then one person at the end of the chain actually has the modification rights you care about. So defenses, all is not lost. I mentioned event log stuff. The difficulty is you have to have your event log tuned at the time the backdoor is actually implemented. So if you find these backdoors in your environment and you don't have, it was put in 5 years ago and you don't have historical information, you're not going to know who put it in, even if you can tell it's malicious. For example, though, tune up your domain controllers now with event log logging. We're actually going to put out some guidance on how to tune with SACLs and event logs for every single attack primitive we talked about. We're not bad guys, we promise. We want to give the full, complete defensive information and bring attention to this problem. So that guidance will be out in the next couple of months. But for example, event log 4738, a user account was changed and then filtering by the property modified for, say, service principal name or something like that. Also, we've been diving into some replication metadata. I have a post coming out in a couple of weeks on this. But when domain controllers replicate data between each other, there's information that's kind of left over, this metadata that says, hey, these properties changed. So using this replication metadata, you can figure out when a property was modified, and you can tell which domain controller the modification originated on. So you can use this to figure out, oh, crap, there was something put in here, and then go straight to that one particular domain controller. And if you have event log tuning, you can figure out who did it. So again, points you in the right direction, but doesn't give you the full picture. You have to have event logs for it. There's not really another way to do kind of forensics on the ntds.dit. Also, SACLs. So we didn't really cover these, but these system access control lists, they're ACEs that specify the types of access attempts that generate audit records in security event log and domain controller. So basically, you can build SACLs that would produce additional, more granular events that say, hey, somebody modified or tried to modify these particular properties. So a lot of people think oh, there's just we don't want to use SACLs, and these have been around forever, but almost no one we see uses them, probably because they think we have to SACL everything and it's so much data and blah, blah, blah. What we think is you can start building SACLs that actually target just the object takeover primitives. So then you can generate just those events, and you're cutting down 1 to 2 orders of magnitude or more the actual data you're gathering. So again, we want to build a complete guide on how to use SACLs to actually detect everything we're talking about. At least and again, that's for modification. If the backdoor is already there, that's much, much harder to actually detect. And there's a little more information that bit.ly link, and we're going to have a post out the next few months. Future work, we tried to implement null DACLs for Active Directory objects because we thought it'd be funny. But if we try to manipulate that, and also there's a bit in the header control bit, se DACL present. But any attempts to modify the NT security descriptor in that way on an object remotely, those bits are ignored from what we can tell. So we might be able to do it if you have codecs, a system on a DC, but we can't actually do it remotely. So this warrants another look. We want to look into that. We also want to research additional control relationships. Again, we are not saying our control object takeover taxonomy is complete. We want to expand it. So credits, huge shout out to our workmate at Spectre, Lee Christensen, Tifkin. He really helped us with some of the labs research and reviewed the white papers and all that. Jeff Dimmick was awesome on doing content review. Everyone else at SpectreOps, we owe our team a huge amount. We did not do this on our own by any means. Also Matt Graber, who used to work with us, he did some great review and did the kind of content feedback and everything. So I think we have, maybe like 3 minutes or something like that? 4 minutes. OK, so we should have some time for a couple questions if anyone's interested. Hopefully we scared you just a little bit, but we want to bring attention to this whole thing. No? No questions? Well,
if anybody's walking up or thinking about walking up, a few other people that I would just like to repeat our thanks for. Luca Bouillot and Emmanuel Groff, formerly from ANSI. Mark Gamache at Microsoft. Robin Gramberg at Microsoft. Vincent Latou, we can't thank him enough. All of us owe him a lot. Benjamin Delpy, the list goes on and on and on.
But yeah, thank you.
Thank you.